Today we're going to talk about polynomial operations and binomial expansion with Pascal's triangle. We learned about the difference of perfect squares and perfect square trinomials when we were factoring in Unit 3. You can use those patterns in the opposite direction for multiplying binomials. When you take a binomial and you cube it, you get the following expansion. That might seem a little obscure to memorize, but hopefully when we look into Pascal's triangle, recognizing the pattern can be a lot more efficient than actually multiplying out the binomial or memorizing the expansions. Number 1, Part A. Because there is a subtraction symbol in between these polynomials, we must distribute the -1 into the second polynomial, which would be multiplying -1 by each term in the second polynomial. Now we can write the polynomials without parentheses. Combine like terms, and you have your answer. You may notice that in Part B, we have a minus b times a plus b. That's difference of perfect squares. So when you multiply that, you get a squared minus b squared. In this case, a is 4x and b is 3, so you get 16x squared minus 9 as your result. Here we have a binomial squared. That expands to be a squared minus 2ab plus b squared. A is the first term, b is the second term. Plug those in and simplify. For Part D, we have a binomial times a trinomial. Each term in the binomial needs to be multiplied by each term in the trinomial. Now distribute. And then combine like terms. And there's your answer. For number 2, find the following products. We have a pattern for x plus y quantity squared and x plus y quantity cubed. Go ahead and expand according to that pattern. Now to get x plus y quantity to the fourth, I need to take the expansion of x plus y quantity cubed and multiply it by the binomial x plus y. This means I'm going to double distribute. Multiplying everything by an x will just add 1 to the exponent of x in each term, and multiplying everything by a y will just add 1 to the powers of y for each term. And to keep it organized, I'll write the x always before the y in these products. You only have like terms when the power of x matches the power of x and the power of y matches the power of y. So 3x cubed y can only be combined with another x cubed y term. An x squared y squared term can only be combined with another x squared y squared term. An xy cubed term can only be combined with an xy cubed term. Simplify. And we have our expansion of x plus y to the power of 4. What about x plus y to the power of 5? That would mean we multiply this by x plus y. That would take a lot of work. So go ahead and just watch me do the work and write down the answer. Now imagine if we had to expand with not just x plus y. something like 3x minus 4y. That sounds like it would get insane. So let's see if there is a pattern here that we can follow to make binomial expansion a little bit more efficient. So let's take a look at the expansions. X plus y to the power of 0 would just be 1. X plus y to the power of 1 would just be x plus y. X plus y to the power of 2 is such. X plus y quantity cubed expands to be this. X plus y quantity to the 4th expands to be this. X plus y quantity to the 5 expands to be this. Now let's take a look at the coefficients of each of our terms. It looks like these coefficients actually have some symmetry, right? 1, 2, 1, 1, 3, 3, 1, and so forth. You must write these coefficients in the initial binomial expansion. Once you continue to simplify, these may not be the resulting coefficients, but they must be there in the initial expansion. Look at this. All these coefficients form the shape of a triangle. This is called Pascal's triangle, and you can easily create it at any time because it has a really easy pattern with the sums. The 0th row, meaning x plus y to the power of 0, has one coefficient of 1. The coefficients of x plus y to the power of 1 are 1 and 1. The coefficients of x plus y to the power of 2 are 1, 2, and 1. But if you didn't remember that, you can always remember that Pascal's triangle follows this pattern. We always start and end with a 1 in each row. And the coefficient below can be found by adding the coefficients directly above it, meaning 1 plus 1 gives me 2. 1 plus 2 gives me 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. The coefficients for x plus 1 quantity cubed are 1, 3, 3, 1, found in the third row. Your top row is the 0th row because it represents x plus 1 to the power of 0. Here's your basic binomial expansion pattern for a plus b quantity to the power of n. The first term is a to the n, b to the 0. Each of these little hexagons represents the numbers from that particular row of Pascal's triangle. But the powers of the exponents go in this particular pattern. A to the power of n times b to the 0. The next term will have a to the power of n minus 1 times b to the 1. The next term, a to the power of n minus 2 times b to the 2. And it continues in this pattern. The sum of the powers for your initial expansion should always be n. N plus 0 is n. N minus 1 plus 1 is n. N minus 2 plus 2 is n. The powers of the first term always descend by 1, and the powers of the second term always ascend by 1. Because we are expanding this polynomial to the power of 4, we will use the coefficients in the 4th row of Pascal's triangle. That would be 1, 4, 6, 4, 1. So for 3x minus 1, a is equal to 3x and b is equal to negative 1. Watch out for the sign of that number. If it's negative, that means your signs will alternate in your polynomial. We're going to write b as negative 1, and as we simplify, the order of the signs will reveal itself. Our pattern should be a to the power of 4 times b to the power of 0. The next term will have a to the power of 3 times b to the power of 1. The next term will have a to the power of 2 times b to the power of 2. The next term will have a to the power of 1 times b to the power of 3. And the final term will have a to the power of 0 times b to the power of 4. At this point in time, check to make sure the exponents in each term add up to be 4. Now, until we know the signs, each of these will be addition. Our first term is a product of 1 times 3x to the power of 4 times negative 1 to the power of 0. Remember, 3x product to the power of 4 is 3 to the power of 4 times x to the power of 4. That's 81x to the 4 times 1, which is 81x to the 4. Our next term is 4 times 3x to the power of 3. That would be 3 to the power of 3, which is 27, times x to the power of 3. This is all times -1, so now instead of having a plus sign, we have a minus. 6 times 3x squared, that would be 3 squared times x squared. -1 to the power of 2 is positive, meaning this term is positive, so we put a plus sign. -1 to the power of 3 is negative, so this term is negative. 3x to the power of 0 is 1. -1 to the power of 4 is 1, so your last term is positive 1. Do the remaining simplification. So you can see when you have a binomial that involves subtraction, your signs will alternate. Positive, negative, and so on. Notice how your coefficients are not the same as Pascal's triangle anymore. That's because one of the terms in your binomial had a number, 3x. That's going to change the ending coefficients of your expansion. Remember, Pascal's triangle only gives you those initial coefficients for the expansion. Then once you continue simplifying, you may get much bigger numbers as your resulting coefficients. And lastly, notice how our exponents always added to 4? That was for the initial expansion. We notice that if we're expanding to the power of 4, then x to the power of 4 will be our highest exponent. But if this binomial had a power in it like 3x squared, then you would definitely have a higher degree in your resulting expansion. So keep in mind that the binomial expansion pattern helps you begin with your expansion, and then you use algebra to simplify each term. This binomial was to the power of 4, so we should have 5 resulting terms. If it were to the power of 5, we'd have 6 resulting terms, and so on. So here is our resulting expansion.